Let's be real, we are swimming in information that's just flying through the air all around us. Music, our phone calls, all our internet data. It's all traveling on these completely invisible highways. So today, we're going to pull back the curtain and see exactly how these signals actually get from point A to point B. All right, let's get into it.
I mean, it's a great question, isn't it? You flick on the radio, and boom, there's music. You tap your phone to connect to Wi-Fi, and suddenly the entire internet is right there in your hand. It honestly feels like magic, but what it really is some incredibly clever physics at play. So, how does it all actually work?
Well, to understand the journey these signals take, we first need to get a handle on the basic rules of the road. You can think of these as the fundamental principles that control how all of our wireless information gets around.
Okay, so the vehicle for all this information is something called an electromagnetic wave, or EM wave. And the best way to picture this is to imagine tossing a pebble into a perfectly still pond. You know those ripples that spread out? That's basically what an EM wave is, just spreading out through invisible fields, carrying energy and information away from the source.
Now these waves have two main tricks up their sleeve: reflection and refraction. Reflection is the easy one to get. The wave just hits something and bounces off, kind of like light hitting a mirror. Refraction is a little different. That's when the wave passes through something, like a layer of our atmosphere, and it bends. And believe it or not, these two behaviors are the key to pretty much everything that follows.
So let's start with our very first invisible highway, the one that stays closest to home. This is our ground-up approach to sending a signal.
And this is what's so wild about them. Instead of just shooting off in a straight line, these ground waves do something amazing. They actually bend and follow the curve of the Earth. It's this ability to hug the ground that lets them travel way beyond what you can see on the horizon.
So the secret here is that ground waves work best at lower frequencies. Now, frequency just means how many waves are passing by every second. Low frequency waves are really long and stretched out, which is what gives them that special ability to bend over hills and just follow the planet's curve. Your local AM radio station, that's a perfect example. That signal is a ground wave, following the terrain all the way to your car radio. But it does lose steam over distance, which is why you can only pick it up for, maybe 50 or 100 miles.
But what if you need to go farther than just across town? Well, for that, we've got to look up and use the sky itself as a giant invisible mirror. So let's check out our next path and see how this works.
This is where things get really, really cool. We can actually aim a signal up at the sky and have it bounce right back down to Earth hundreds or even thousands of miles away. Our own atmosphere becomes a kind of natural satellite dish. And this shows the journey perfectly. A transmitter on the ground shoots a signal up. It travels until it hits a specific layer in our atmosphere, which acts just like a mirror and reflects it. That signal then comes back down to a receiver way, way over the horizon. It's a lot like skipping a stone across a pond, except the pond is the planet and the stone is a radio signal.
And this slide right here helps explain a really common mystery. Have you ever been driving late at night, scanning the radio, and you suddenly pick up a distant AM station super clearly? That's because the layer of the atmosphere that reflects these signals, it's called the ionosphere, it gets much more stable and mirror-like after the sun goes down. During the day, the sun messes with it, but at night, it settles down, giving us a perfect surface for a long-distance bounce.
Okay, so we've hugged the ground and we've bounced off the sky. Now for the final path, the one that powers most of our modern wireless world, the straight shooter.
So unlike ground waves that curve or sky waves that bounce, these signals, we call them space waves, travel in a perfectly straight line. They act a lot more like a beam of light from a laser pointer. If anything gets in the way, like a mountain or even just the curve of the Earth, that's it, the signal is blocked. And this right here is the workhorse of our modern age. Your FM radio, your TV, your Wi-Fi router, your cell phone, all of them use these line-of-sight space waves. They operate at really high frequencies, which means the waves are short and packed together. That lets them carry tons of data, perfect for video and internet. But it also means they can't bend around stuff. And that's why we put cell towers and TV antennas way up high, to get the clearest possible shot to your device.
So to wrap it all up, we've got three totally different ways that signals travel. We have the ground waves for local stuff, sky waves for super long distances, and space waves for all the high-speed signals that power our world today. Each path is a different tool for a different job.
When you step back and really think about it, it's just remarkable. We've actually learned the rules of these invisible waves and figured out how to use our own planet and its atmosphere as part of the system to send messages just about anywhere we want.
And that brings us to a final thought. We rely on these highways more and more every single day. But just like real roads, they have a limited capacity. As we keep sending more and more data flying through the air, the big question for the future becomes, what happens when our invisible highways start to look like one giant global traffic jam? It's a challenge we're all going to be navigating together.